Hello everyone and welcome to this call. My name is Robert Molz and I'm happy to present to you a project I've worked on in the beginning of the year. So the purpose of the project was to showcase how to combine CAM machining and robotics to create automated manufacturing solutions. And this project was done in context of the Intertech trade show in Bern, Switzerland. So this trade show is mostly about manufacturing in general, but with a heavy focus on machining. So the idea for the project was, as already mentioned, to combine CAM machining and robotics to automatically produce this part that we see here, which is a machined helmet mounted on a 3D printed stand. And the manufacturing cell that was planned to do this consists of a 5-axis milling machine, a FANUC robot, an assembly station, a storage for raw materials, and a station where the machined part can be deburred and polished. So the task of the robot is not only material handling, so it will also assemble the machined part and 3D printed stand, and it will deburr and polish the machined helmet. When we look at this cell from this perspective of how to handle it in 3D experience, so we have CAM Robotics to do the overall orchestration of the manufacturing cell, as well as the loading, unloading, and assembling of the parts. And we have CAM Machining to program the milling machine and to program the deburring and polishing operations with the robot. Here I want to take a closer look at the team behind this project. And one very important aspect of that is that everything was done on the cloud. And this allowed us to collaborate across country borders as well as domain borders. So since this project was brought to us by one of our machining partners in Switzerland, the project leader was located in Switzerland. We had Loic Sandras from the IPS team support us in everything regarding to robot programming. So he did the assembly parts and the material handling with the robot. Then from our partner in Switzerland, we had one CAM programmer who programmed the 5-axis milling machine. And myself, I was doing the deburring polishing operations with the robot in CAM machining. The project itself was done in 4 stages. We have planning, programming, validation, and implementation. Each of those stages representing its own challenge. And here I want to focus on first programming. So we don't want a machine to run for too long since it's a trade show and we don't want people to get bored. So what we need is a reliable and very efficient toolpath. And secondly, we need to be able to program those machining toolpaths for the robot, which using robotics applications is not straightforward. But since in machining we now have the capability to program also robots, I will show you how that can be done. So first of all, for the machining, first stage, of course, is roughing. There the bulk of the material gets removed. And we are able to do that with a very efficient 5-axis roughing strategy, which allows us to keep the tool as short as possible. And we can see here the machine moving away from the tool when we get further down, so as to avoid any collisions. And of course, roughing is only half of it. After the roughing comes, of course, the finishing to machine all those details that we can see on the helmet. And the challenge here is to confine those finishing or detailing toolpaths to exactly those areas where we have material left over, so as not to machine air or do unnecessary cutting movements. And this we can see done here. Next, we have to take care about deburring and polishing the part. So by supporting the robots in CAM machining, we bring basically the toolpath technology from CAM machining to the robotics world. And yeah, in the robotics world, we already have quite extensive library of robots that we can use in the robotics applications, but now as well in the CAM machining application. And what we are doing here is we are programming a standard 5-axis toolpath to deburr the zone where the helmet was attached to the stock material. And we can see this done here. And the special thing here is we can see that the tool is stationary and the robot moves the part against the tool. So something that's called in robotics a fixed TCP application. So meaning that the tool is fixed and the part moves relative to the tool. So and we can then see the result here. So the burr from where the part or the helmet was broken off the stock material has been removed by the grinding wheel. Next step is validation. The challenge here is to make sure that the robot as well as the machine run without any collisions. And especially in case of the robot also, we have to make sure that we stay within the axis limitations, because with robots, if we rotate our axis too much, it could be that we rip off a cable or anything like that. And that, of course, needs to be avoided, especially taking into consideration the tight schedule for implementation. So what we can see here is the NC code simulation for Delmia machining. So we can simulate the machine based on the actual NC code that will be put on the machine and run. So if we don't see any collisions or problems here, then we can be very confident that also it will run correctly on the machine. In robotics, again, we had the support from Loic, and what he did was to connect the virtual robot controller directly with the simulation in Delmia. And what that allows him to do is to load the robot program and then drive the simulation in Delmia machining with that program. And this way we can then, of course, detect if the program will cause any collisions and if the access limitations are respected. So that is very important before we go on the machine for the first time. We need to be sure that everything is in order. Otherwise, we would not be able to keep those tight deadlines. So then the last step would be the implementation. So here, of course, as I mentioned, we have a very tight deadline. So the whole project was done in about 8 weeks. And because of that short deadline, there was also no chance to do any test runs before everything was assembled on site at the Innotech trade show. So here we can see the complete process that was shown there. So first the robot is loading the part into the machine, blowing off any chips from the vise so as to make sure the part is securely held. Then the machining starts. We can see some machining operations here. So once the machining is done, the robot picks up the part that's still attached to the stock material, places it in a station where the part can be detached from the stock, changes then to the form gripper to grab the part from the inside, rips off the part. Then the next station is the deburring, as we've already seen, to remove the burr that's left when we rip off the part. Then after that is the polishing. So these two operations have been done using Delmia machining. And next would be assembling. So we place the helmet in the fixture, pick up the stand, assemble both of them together. This part has been done in Delmia machining, in Delmia Robotics with the help of Loic. And then the whole assembly is turned over and placed into its storage. So thanks to our VNR capability and to the collaboration of the cloud, after the whole equipment was delivered, it took only 4 days to build it up and get it production ready with the programs that we delivered from Delmia Robotics and Delmia Machining. And so here's a quick summary of what we did. So first in the planning, we built a digital mockup to confirm that all the stations are reachable for the robot. Then we did the programming, so for robot and machine, the validation that needed to be done before anything could go on the machine, and then the implementation, which was greatly accelerated by the V+R capability and the collaboration on the cloud platform. And to conclude, what gives the value to our customers, of course, that we are enabling them to implement those automated production solutions, help them to decrease time to market, reduce cost, and be more flexible in production. So thank you very much and goodbye.